Good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. In previous class, we saw long questions on modes of heat transfer. So in this class, we'll see problems, uh, problem solving on modes of heat transfer. We'll see different modes, different problems which are given in the question bank. We'll discuss those. Basic for the problems, this one, for the modes of heat transfer, that three modes: conduction, convection, and radiation. Those to measure the rate of heat transfer through conduction, convection, radiation, there are three laws are there. For conduction, Fourier's law is there. For convection, Newton's cooling law is there. For radiation, Stephen Boltzmann law is there. Okay. So he has given Fourier's has given formula Q is equal to minus Ka into dt by d small. Okay. Newton has given Q is equal to Ha into delta. Stephen is given Q is equal to sigma A t to the power of. Okay. So based upon this formulas, we will solve the numericals. Okay. The first one, stainless steel plate, thickness is 2 centimeters, is maintained at a temperature 550 degrees Celsius at one phase and 50 degrees Celsius other phase. The thermal conductivity of stainless steel, thermal conductivity also given, that is 19.1. Suppose this is the body, stainless steel, the thickness is equal to L is equal to 2 centimeters, convert into meters, 0.002 meters. So temperature T1, that is given 550 degrees Celsius. Temperature T2, that one given, so 50 degrees Celsius. Okay. Thermal conductivity also given, K. The K is equal to 19.1 watt per meter. So what I have to find out, count the rate of heat transfer according to Stephen Boltzmann law. Q is equal to minus Ka into dt by dx. So minus Ka, K is given, area also given. You have to find out the per unit area. It means you can write like this one, that is the heat flux. So Q by A is nothing but small q is equal to minus K into temperature difference, means so T2 minus T1, then by dx, thickness is equal to L. So it means so minus means so T1 minus T2 into K by L. T1 is equal to 550 minus 50 by L is equal to 0.002 into thermal conductivity. So that is equal to 19.1. Here you can write like this one here, 19.1. Then you get the answer, that is the value is equal to Q is equal to 477.5 watts per meter square Kelvin. So this is the answer. So in this way you can solve this type of numerical. Next we will see one more numerical. The flat plate of length. So length of the plate is given, L is equal to 1 meter and width is equal to B, width is equal to 0.5 meters. So L into B is the area. So place it in airstream, fluid temperature 30 degrees Celsius and blowing parallel to it. So the convection heat transfer coefficient H also given, which is equal to 30 watt per meter square Kelvin. Okay. So calculate the heat transfer if the plate is maintained at a temperature. So temperature of the plate, so TF not TS, temperature of the solid surface, that is 300 degrees Celsius. You know this one according to This is related to convection process. According to convection, Q is equal to HA into temperature difference T1 minus T2. Okay. H is given, that is the value of 30 into area is equal to L into B 1 into 0.5 meter square. Okay. Into temperature difference. So temperature is equal to solid surface temperature 300 minus fluid temperature is equal to 30. If you solve this one, you will get 5.55 kilowatts. Okay. So in this way, just you can solve the numericals. We'll see one more numerical, which is related to radiation. A radiator in domestic heating system operates at a surface temperature, that is the surface temperature Ts, T is equal to 55 degrees Celsius, convert into, because it is the power of fourth power of the absolute temperature. For the powers, you should convert centigrades into kelvins, that is 328 Kelvin. Determine the rate at which it emits heat per unit area. Per unit area means Q by A, that is heat flux, is equal to, the formula. Q is equal to, according to radiation, Stephen Boltzmann law formula, sigma A into T to the power of 4. Then Q by A is equal to small q is equal to sigma into T to the power of 4. Okay, sigma into T is the 328 to the power of 4. Sigma value is equal to 5.67 into 10 to the power of minus 8 into 328 to the power of 4. Then this value is equal to nearly 0.066 watt per meter square. Okay. You can verify this one also. In this way, just you can solve the different numericals. Next one is the an insulated pipe 50 outside diameter. Diameter D is given 50 convert into meters 0.050. MCVT also is equal to 0.8. Okay. Is laid in a room at room temperature T fluid. You can take 30 degree Celsius. If the surface temperature is equal to Ts is equal to 250 degrees Celsius. The convective heat transfer H is equal to also given, that is 10 watt per meter square Kelvin. Calculate the heat loss per unit length of the pipe. Unit length of the area is equal to L is equal to 1. Then area of the pipe is equal to pi dl. You can take pi into d is equal to 0.05 into L is equal to 1. You can find out the area. Then Q is equal to, you can find out HA into T S minus TF. H also given. H is equal to 10, area is equal to pi d, L into Ts is equal to 250 minus 30 degrees. Okay. We will get this value 8182.8 watt per meters. Okay, this is the. So another numerical will say a surface is at 200 degrees Celsius and as area, surface temperature Ts is equal to 200 degrees Celsius. Area of the surface is equal to 2 meters. Or it exchanges heat with another surface, okay, at by radiation. One surface, this is another surface. This one is the area A1. Okay, exchanges heat with another surface B. This is A, this one is the B. This temperature is equal to TA. TA is equal to 200 degrees Celsius. TB is equal to 30 degrees Celsius. The value factor due to the geometrical location emissivity. Factor and view factor and emissivity is equal to 0.46. Okay. Determine the heat exchange. Also find the value of thermal resistance and the equivalent to convective heat transfers. Okay, so this thermal resistance also you have to find out, and HR also heat transfer coefficient also you have to find out. First of all, through radiation you have to find out the Q value. You know the formula of Q. Q is equal to sigma area. If you consider both areas are same, then Q into sigma A, area also given, into uh, emissivity epsilon. You can take U factor also you can take into T1 to the power of 4 minus T2 to the power of, or Ta to the power of 4 minus T2 to the power of 4. Convert into 273 for the conversion of Kelvin. Here also 273. Okay. So if you substitute these values, sigma 5.67 into 10 to the power of minus 8 for this one, the area 2 epsilon 0.246 into temperature. Uh, Temperature is equal to 473 to the power of 4 minus 303 to the power of 4. Okay. If you solve this one, you will get this answer. Q is equal to 2171.4 watts. Okay. So this is the rate of heat transfer through radiation. So same Q for the convection also. You can use this Q rate of heat transfer to find out the thermal resistance. You know the formula for Newton's cooling law. For the convection, Q is equal to HA into delta T. Okay. Thermal resistance is equal to delta T by 1 by HA. So we have to find out this one. This is called RTH. So then RTH is equal to Q by, no, RTH is equal to delta T by Q. Delta T is the temperature difference. You know this one. That is the 200 minus 30. So 170 degrees Celsius by Q value is equal to 2171 per 4. Okay. If you take this one, automatically you will get the thermal resistance. Thermal resistance is equal to 0.07828. Okay. Then you can find out the HR also. HR, and it means H also you can find out. You know the area and delta T and Q also. Then you can find out H. So H value is equal to 6.38 watt per meter square Kelvin. Meter square Kelvin. You can solve like this one. We'll see one more numerical. So a plane wall is 150 thick, and its wall area is 4.25 meters square. If its conductivity, so conductivity K 9.35 watt per meter square, meter Kelvin per meter degree Celsius. Okay. Surface temperature Ts is equal to 150 degrees Celsius. So a plane wall 150 thick, one temperature. Suppose this is the plane wall. This is T1, this is T2. T1 is equal to 150 degrees Celsius. TT is equal to 45 degrees Celsius. Okay. Thermal conductivity also given, and area also given. Area given, K also given. Then you can find out the what you have to find out. Heat flow across the plane you have to find out. Next to temperature gradient in that flow. According to this is the conduction principles, because thermal conductivity is given. So two temperatures also given. You can find out Q is equal to, according to Fourier's law, minus Ka into dt by dx. Okay. So temperature, if you change the temperature, so then Ka into temperature T1 minus T2 by thickness. What is the thickness? A plane wall thickness is equal to 150 converted to meters, 0.15 meters. Okay. That is the thickness. K into thickness. K also given. K value is equal to, you can write here Q is equal to. So K is equal to thermal conductivity, that is 9.35 into area. Area is equal to 4.5. It means so 9.35 into 4.5 into T1 minus T2 by thickness is equal to 0.15. Okay. If you solve this one, you will get the value that is called 29452.5 watts. So this is the value. Okay. So next we will see the temperature gradient. Temperature gradient. What is the value of temperature gradient? So temperature gradient according to conduction process, Fourier's law. So temperature gradient to dt by dx. So Q is equal to minus Ka into dt by dx. So we have to find out this one. Then dt by dx is equal to Q by Ka. Q by Ka. So Q already you know that 29452.5 divided by K, thermal conductivity 9.35 into area, that is 2. If you solve this one, then you can find out the value. So that is minus 700 degree Celsius per meter. So in this way, just we can solve the different numericals based upon the modes of heat transfer. Mainly the 3 laws of modes of heat transfer. So this is one more example. The roof of an electrically heated home. The roof measurements also given 6 meters long and 8 meters width and 0.35 meters is the thickness. 0.35 meters is the thickness. So length also given, width also given, thickness also given. Okay. Thickness. So thickness also given. Just then you can find out the area. So area of that roof. So and it is made of flat layer of the concrete whose thermal conductivity. So thermal conductivity of this one also given, the K. K is equal to 50.8 watt per meter Kelvin. Okay. So the temperatures, inner surface temperature, outer surface temperature, T1 is equal to 15 degrees Celsius and T2 is equal to 4 degrees Celsius respectively. Okay, so the heat is applied, it means through electrical power, that is the time duration is equal to 10 hours. We'll see first rate of heat transfer. So Q value, the thermal conductivity of the proof, that is given, nothing that heat transfer through roof by conduction. You know this one, conduction process, but it is solid. The area also given, that is the length into width, that is 6 meter into 8 meter, that is 48 meters square. Steady rate of heat transfer, we will see, we will find the Q value. Okay. So Q is equal to, you know this one, to find out the Q value. Q is equal to minus K into dt by dx. Minus means minus K value also given. So K is equal to the value 50.8 into area also given, that is the 48 meters square. 48 meters square into dt, temperature difference also given, 15 minus 4 divided by thickness also given. So thickness of this plate is equal to 0.25 meters. Okay. So in this way, just like we can find out the Q value. Okay. So then we have to find out the one night measured, okay, for the period of electrical energy for the 10 hours. 10 hours. It means that is the Q rate of heat transfer into number of hours. So energy is equal to Q into number of hours. So time is equal to Q. This is the Q. Q value is equal to 107.289 into. So time is equal to 10 hours. 10 hours. Then the values is equal to, you can find out. So this is the amount. The amount of energy into unit cost is equal to total. So this one is the amount of uh, this charges to heat that roof. You can solve this one. Okay. So we'll see one more numerical. An insulated pipe, 50 outside diameter, MCT also given, is laid at room at 30 degrees Celsius. Insulated pipe. The surface temperature also given. Heat transfer coefficient also given 10 meters. Okay. Calculate the heat loss per unit to pipe. Unit pipe. Okay. Insulated pipe, outer diameter also given. So that is the 50 mm. It is this is outer diameter temperature, that is the Ts is equal to 50 to 25 degree. Surface temperature is 25 degrees Celsius. Room temperature Tf is equal to 30 degrees Celsius. So heat transfer takes place from the solid to fluid, means you have to consider the convection process. So convection process heat transfer coefficient also is given, that is the 10 watt per meter square. Okay. Then you have to find out the here heat transfer takes place by convection process and radiation process also. First of all, you can find out the convection process, then you can find out the radiation process. Area is equal to pi dl. Diameter d is given. Length means unit length means L is equal to 1. You can consider this one. Okay, you can find this value here. So Q convection you have to find out first. HA into Ts minus T alpha. H, that is given 10. Area pi dl. Diameter given. Length also 1. And temperature is equal to 30. This one is the 25 degrees Celsius. Okay, if you find out this one, you will get to Q conversion values. Next to Q radiation. So this is the radiation. Sigma epsilon T area into Ts to the power 4 minus T alpha. It means room temperature, solids surface temperature to the power 4. Okay, so this is the value we can calculate this one. Okay, so these are the different books you can refer this to solve different numericals based upon the conduction process. Thank you listening this class. We'll see in next class fundamentals of different analytical questions or problem solving some conduction process. Thank you, listening.
Like, share and subscribe. Hit the bell icon for more updates.